the opposite here. Okay, for example, 5 grams of nickel 2 chloride hexahydrate is dissolved in enough water to give 250 milliliters of solution. What is the molarity of the solution? Okay, first thing I want to tell you, when you see grams and someone's asking you about molarity, you know right away that molarity is moles per liter, right?
Right.
So you're not going to plug in the number 5 on top of here because that's not moles, that's grams, right?
Right.
So the first thing I want to do is calculate the moles of nickel 2 chloride hexahydrate. And when you calculate the molar mass of a hydrated ionic compound, the water molecules in that compound are part of the molar mass of that compound.
Right.
Now while you guys are working on that activity, I went through here and decided to calculate that molar mass, save a little time. Okay, so this was the formula. I have 1 nickel, 2 chlorines, 12 hydrogens, and 6 oxygens, right? So I did all my math, and there's my molar mass, 237.686 grams per mole. So to figure out the moles of the nickel 2 chloride hexahydrate, I'm going to take these 5 grams of the compound. I'm going to put 5. I'm going to skip the formula now for time here, and then divide it by what? What should I do with that molar mass? Tell me what goes on top and what goes in the bottom from this number.
So 237.686 grams goes on the bottom, and then on the top you have 1 mole.
Exactly. Okay. So this is the compound here. I didn't want to write it out for time, but it's the grams canceled out, I get moles. So if you're given a mass of something and want to figure out a concentration in molarity, you have to first calculate the number of moles for that compound. So we'll just plug that in and see what we get. 237.686. Here's what I get. Anyone else? I heard 1 yes, so that's usually good enough, but anyone else get that number? Okay. I'll just write out a whole bunch of sig figs for now and round in here later at the end. So that's my moles of my whole compound, right?
Yes.
But the question asks, what is the molarity?
So you divide that by 0.250 liters.
Exactly. So I'm going to just write it on the board here. So molarity equals moles over, I'm going to put the volume in liters, okay? Just simplify it, say moles per liter. Moles of solute per liter of solution, right?
Right.
So here the volume is given in milliliters, isn't it?
Yes.
So I have to convert that milliliters into liters first. I can do that in my head because I know it's 1,000, or I can do it on paper and do that conversion. I'm going to do it in my head, okay? So 250 milliliters equals 0.2500 liters, right?
Yes.
Does that make sense what I'm doing there? As Crystal was saying as well, I just want to make sure everyone followed it, okay? So take my moles divided by my liters, my total volume of solution, to get my molarity. Now in this case, I'm just going to divide it by 0.2500. And here's what I get for my concentration of that particular solution.
Yes.
So here 1 yes. Anyone else? Okay, that's good. So how many sig figs do I have? 3 sig figs here. 0.0841, right? Molar nickel 2 chloride hexahydrate. I will tell you, when you dissolve a hydrated ionic compound like this in water, the water molecules, they basically go into the water solution, okay? They start out in the crystal lattice of the hydrated ionic compound, but once they dissolve, they're not around anymore. They're not associated anymore with this compound because the cations and anions of the ionic compound come apart, don't they?
Yes.
Any questions on this problem? Is this anything like the stuff you were just doing here in this activity? It is, yes.
If there was another question asking us for the molarity of chlorine, could we just multiply that final molarity by 2, or would we have to multiply the moles by 2 and then divide by 0.2?
You can take final molarity, multiply by 2. You can do it here or you can do it later.
Okay.
It's 2-to-1 ratio.
Okay.
Which is another thing that you learned about in this activity, right?
Mm-hmm.
Which actually, this part right here is the same idea that you just learned about. So this is kind of a review for the quiz on Thursday from what's in the activity. So here I have sodium nitrate, an aqueous solution of sodium nitrate. What does that mean? It means the cations and anions dissociate out into +1, -1, right? The polyatomic ions, as you know from the sulfate example in the activity, stay together. They do not come apart into, like in this case, nitrogen and oxygens. So NO3 -1 stays together as a polyatomic ion with a net -1 charge. So if you make a solution that is 0.3 molar sodium nitrate, it means that the sodium cation concentration the nitrite anion concentration are both 0.3 molar. How do I know that?
Because
Because-
the equation is balanced.
Yeah, because in 1 mole, when I have 1 mole of NaNO3, I have 1 mole of sodium and 1 mole of nitrate, right? In that dissociation process. So the concentrations of both the cation and anion are the same. However, if I instead make a solution of potassium carbonate, now notice the potassium carbonate formula, I have K2CO3, right? That means when it goes into solution, it dissociates into cations and anions. I get 2 potassium cations for every 1 carbonate, right? How do I know that? Because of that 2 right here. So if my potassium carbonate concentration, and by the way, when you see a formula with brackets around it, that brackets means the concentration of that compound. Okay?
Okay.
So it's 0.1 molar in that little compound, right? But what is the potassium cation concentration? If the compound itself, the whole thing is just, we say the whole thing is 0.1.
You'd multiply it by 2.
Multiply by 2, because you can see here, there's 2 potassium cations per 1 mole of this, right? So this concentration is going to be 0.200 molar. So write that in, right? If you have the notes, which I assume most of you do. What's the concentration of the carbonate anion in that solution?
0.1.
0.1, right? Hopefully everyone in the room is going, yeah, that makes sense, I just did this stuff. What mass of oxalic acid, that formula shown there, is required to make 250 milliliters of a 0.0500 molar solution? So people write capital M like that, they'll say a 0.0500 molar solution is how you say that. Well, our concentration of molarity is moles over volume, which of course our volume is going to be liters, right?
Right.
So if I want to do this algebraically, it says, well, let me just have this algebra down here. So if I want to figure out moles, I just take molarity times volume. So I take volume multiplied by both sides, cancels out, right? So I just did a little algebra there, didn't I?
Yes.
So although the question's asking for mass, and I have a molarity and I have a volume here, as you can see, right? Is there any way for me to directly, in one set of calculations, calculate the mass? Directly?
No.
Like one simple equation, it's one simple amount? No, there's not, because you know why? Because molarity is moles over liters, right?
Right.
And of course, this is volume in milliliters. So once I figure out the moles, then I can figure out the grams. Does that make sense?
Yes.
Because molarity is moles over liters. Thank you for talking, by the way, when I ask questions. Where's this? So, first thing I have to do is calculate the moles of acid required. Basically in 250 milliliters of a 0.0500 molar solution. So there's a few ways you can do this. I'm going to do it the dimensional analysis way right now. So I first write out the numbers I have. So I have this concentration, right? I have this volume. We already know it's going to be oxalic acid. Agreed?
Yes.
I'm going to skip writing that out. Capital M means moles per liter. Agreed?
Agreed.
Here I have liters. What do I have here for units of volume?
Milliliters.
So maybe I want to do something with that milliliters. For example, I'll do this one on the whiteboard now. 1,000 milliliters per liter. Convert my volume of milliliters to liters because I need to have my units cancel, right?
Right.
Okay, so I have that many liters. I want you to notice something. Moles per liter, liters. What's this thing we're supposed to do first? Calculate the moles of acid required, right?
Right.
So I can use molarity as a conversion factor, just like I use molar mass as a conversion factor and lots of other things as conversion factors, right? You have a unit on top and a unit on the bottom. So I'm going to do this the dimensional analysis way right now. So question mark moles of, and I'm going to write out what it is, oxalic acid equals 0.2500 liters. So far so good? I have one more number I can use, this one right here, right?
Mm-hmm.
And hopefully you'll notice if I leave it written the way it is, on the whiteboard up here, I put moles on top per liter on the bottom, I'll just write L like that. See how the liters cancel out? Liters cancel out, and I get, what do I get? I get moles, don't I?
Yes.
So let's plug that in our calculator, because we're gonna use one step by step right now. 2500. Okay, so I have this many moles of oxalic acid. So I'm using molarity as a conversion factor here. I'll just let you know, I'll just quickly do this over here. I have molarity, don't I?
Yes.
I have volume in milliliters, I convert to liters.
Yes.
Can I solve for moles by plugging in the equation and doing algebra as well?
Yes.
You can do either way you would like, whichever you prefer. If you prefer the unit cancellation way, the dimension analysis method, feel free to use this method. If you prefer to plug in molarity here, 0.2500 liters here, and then do algebra and solve for moles, that's a-okay. Whatever you like. Now I have the moles, but I don't want moles at the end, I want mass, don't I? What's my last step to figure out the mass of oxalic acid required to make up 250 milliliters of a 0.05?
You find the molar mass of H2C2O4.
Exactly. You find the molar mass of this compound, the oxalic acid, which of course I didn't figure out ahead of time, so now I have to figure it out. So for hydrogen we have two of them times 1.008, 0.016. Carbon, you have 2 times 12.01. And oxygen we have 4 times 16, so 64. So I can do that, most of that in my head there. Not to make any math errors, and the rest of it in my head, I'm gonna plug it in the calculator. Here's what I get.
Yes.
Same thing for anyone else, okay? So 90.036. That's my molar mass of oxalic acid. What should I do with that number?
You should take your moles and divide it by that number.
Close. You want to carefully do this, okay?
Multiply it by that.
Multiply it. So that's why I always write my units out, okay? To make sure I'm doing the math right. So 90.036 grams H2C3, C2O4 per mole of H2C2O4. Notice my moles are on the bottom here, on the top right here, so they cancel out, don't they?
Yep.
So every time I do a problem like this on the whiteboard, I always show units, and I know for sure I'm not doing the math incorrectly. I'm multiplying when I should versus dividing when I should, right? So I'm going to take that number times 0.0125, and basically what my answer is 1.1, how many sig figs do we have? 3. So 1.13 grams of oxalic acid. That would be a solid acid. So what does this mean? Like, what if someone wanted to actually do this? Someone said to you, make up 250 milliliters of a 0.0500 molar solution of oxalic acid. And you're like, oh, okay, I'll do that. They expect to know how to do it because you did chemistry a long time ago. Yes? So here's what you do. You would do these calculations like we just did. You would have to say, what does this mean? It means that if I take if I go weigh out 1.13 grams of oxalic acid, and I get a container that can fit at least 250 mils of liquid, in this case water, total volume, right? I'll put that 1.13 grams in that container. I'm going to add water up to the 250 milliliter mark. That's what that means. Make sure it's all dissolved and all mixed together, right?
Right.
Because your total volume of the solution is 250 milliliters. It's not 250 milliliters of water, it's 250 milliliters total volume, because this mass of oxalic acid also takes up a little bit of space, doesn't it?
Yeah.
Any questions? 2 minutes. Not good. Okay, so I want to do one more problem, but I think we're going to be out of time. Let's do one more problem here. This one's the easy one. There's one other one I want to do, but I'm going to do this one instead. Preparing solutions by dilution. Okay, you have 50 milliliters of 3 molar sodium hydroxide, and you want a 0.5 molar sodium hydroxide solution. What do? Well, most of us know that 3 molar is a higher concentration than 0.5 molar, right? I should say most of us, I'm assuming all of us know this, right? So 3 is a big number, so higher concentration, lower concentration. Most of us know what you would do is you would have to add some aqueous solutions, right? is add some water to dilute it. But the question is, how much water would you add? Maybe I shouldn't do this problem. I know it's hard when it's already 1:45, right? Okay, I will not do this problem. So it's already 1:45, and then let's stay over, so we're gonna finish the problem. We'll start this out.